Good morning. Last time we left off, we were finding the rotational inertia of a rod rotating about its endpoint. And we said, let's go ahead and find it now for that same rod rotating about its center point. And we've learned this technique where we can integrate over the rod to find the rotational inertia. We do this a lot in physics. We take a little tiny infinitesimal chunk of the mass, and we say it's so small we can treat it like a point mass. Well, what does a point mass have for its rotational inertia? mr squared. So a little tiny infinitesimal chunk will be the mass, dm, times r squared. So the little tiny contribution to the total rotational inertia, I'll call that di, is equal to dm times r squared. The little element of mass, this little guy right there, times r squared. We integrate, we add them all up, and we get the total I is the integral of r squared dm. Well, we can't integrate dm. We've got to turn that into something we can integrate over. We have to figure out how much mass is in that little tiny chunk of the rod. Well, it's got some length to it. We can call that dx, and it's located over here at a position x. And so we can figure some of these things out. R, let's hit these one at a time. R is the distance from dm to the axis of rotation. I made the axis of rotation the origin. And by making the axis of rotation the origin, then my x, what happened to my x? My x is r. It's the distance from dm to the axis of rotation. So r here is just x. dm, we can take that length, dx, and multiply it by the density, the mass density, lambda dx in this case. In general, it's ds, right? So the length element. If my rod had a curve to it, it would be ds, the length element, the arc length. But here we just have a straight line. And then if it's uniform density, I can plug in m over L for the lambda. If it's not uniform density, you're told what the density function is, and you plug that function in. And what am I integrating over? All the dm's, right, that make up every little chunk of mass that makes up my rod, starting at one end of the rod and going all the way to the other end. I am integrating from minus L over 2 to plus L over 2. Now you ask yourself, is lambda constant? If it is, it comes out of the integral. If it isn't, you plug in the function that you get. Integral of x squared is x cubed over 3. We're evaluating minus L over 2 to plus L over 2. Lambda is m over L if it's uniform density. Got a 1/3 somewhere here, right? And what do I get? I got a (1/12) ml squared. And remember, we talked last time, we expected this to be much smaller than the rotational inertia when the rod was rotating about its endpoint. When the rod is rotating about its endpoint, all of the mass, half of the rod is really far away. When the rod is rotating about its center point, all the mass is in close to the rotational axis of rotation. And it's got this r squared, right? mr squared. Every mass is multiplied by the square of the distance from that mass to the axis of rotation. So if you take some of the mass that's in close and you move it farther away, the rotational inertia goes way up. You should be able to kind of look at different objects and start to spot which one is going to have the biggest rotational inertia. All right, we will do more of these, but let's switch gears and think about rotational kinetic energy. We talked about rotational kinetic energy last time. We have a formula now. The rotational kinetic energy is 1/2 I omega squared. And we can use that now. So what is that? What's one of the first things we can do? We can give our pulley some mass, because we can now account for the energy stored in that pulley as it rotates. So let's take a look at a problem. Let's take a look at our favorite problem. There we go. I probably should put a spring on there too, but yeah, that's okay. We're trying to learn about rotational kinetic energy, and the spring doesn't have anything to do with that. So we'll leave the spring off. If we were given all the information here, the pertinent information, like the masses of block 1 and block 2, and what else? The mass of the pulley and the radius of the pulley. And you need one more bit of information here. You need to know what shape the pulley is. So let's say it's a solid disk. And what else? Theta. That's a theta. And our coefficient of kinetic friction, and the height, and the fact that it starts from rest. Okay, I think that's everything we need to know. And what are we going to find? We will find the final velocity, the split second before it hits the ground, right? Find V final just before M2 hits the ground. So let's set up our energy bar chart. We've got initial energy, mechanical energy. We've got final mechanical energy. And we've got what happens in between the initial state. And the final state. And what kinds of mechanical energy do we have in this problem? Well, why don't I give you a minute to try to set this up? Think about what you'd have in your energy bar chart and then fill it in, and then we'll do it together. Let's take a look at our equation here for the bar chart. How we're going to set up our bar chart. Mechanical energy. So that consists of kinetic energy, gravitational potential energy, and spring potential energy. That's our mechanical energy. Every mass in our system might possibly have kinetic energy and gravitational potential energy. So let's start filling that in. We've got block 1. Block 1 may have kinetic energy at the beginning and might have kinetic energy at the end. Block 2 might have kinetic energy at the beginning, might have kinetic energy at the end. What else has mass? The pulley. The pulley now has mass. We have a third mass in our system. So K, I'm going to put K pulley. That's going to be our rotational kinetic energy. And mass 1 might go up or down. So I've got a UG for mass 1. I'm running out of room here on my... And UG final for mass 1. And a UG for mass 2, gravitational potential energy for mass 2. And my pulley is fixed to the earth, so it's not going up or down. I guess if the pulley was moving up or down, I could have a gravitational energy for the pulley also. But in my case here, in our case, it's not going up or down. Okay. And in between, what could we have? We could have friction working on our block 1. and work done by external forces. I think that's everything that completes our chart. So let's go ahead and fill in our chart here. So here's our plus, 0, minus energy bar chart. Here's our equal sign, right? Let's fill it in. Is anything moving initially? No. Then there's no kinetic energy for block 1, block 2, or my pulley. Are things moving at the end? Yes, they are. And that means they have kinetic energy. Kinetic energy, always positive. So I've got a positive kinetic energy for 1, positive kinetic energy for 2, positive for the pulley. Does mass 1 go up or down from the beginning to the end? It goes up. So I'm going to pick the lowest point in my problem for mass 1 to be 0. I'm going to pick the beginning to be 0. You can pick any point you want to be 0, right, with gravitational energy. But at the end, you have to have more than what you started with. So if I started at 0, a positive number is more than 0, so it has some positive gravitational potential energy. Block 2 goes down. I'll pick the end to be 0. So it started out with more than 0. That's a positive number. Started out with some positive gravitational potential energy. If I had picked 0 as my starting height, my starting point, then how do I get less than 0? I have a negative potential energy at the end, right? As long as it goes less at the end. You can do that with energy, with gravitational potential energy here, because it's a scalar quantity. Do I have friction in my system? Yes, I do, acting on block 1, and friction does negative work. And any external forces? No, I've included the Earth in my system because I have gravitational potential energy, and I have no hands reaching in or one end of a string or anything like that, so no external forces to account for. Now I can write out my equation. This is a tool, helps me get the equation correct. So M2GH, that's that term right there, minus the work done by friction, mu times the normal force times the distance that force acts through, equals 1/2 M1 V final squared plus 1/2 M2 V final squared. Remember, they're all moving at the same speed because they're connected by a string. So when one moves 1 meter, the other one moves 1 meter. When one of them moves 1 meter per second, the other block is moving 1 meter per second. And now I have my rotational kinetic energy, 1/2 I omega squared. And I'm missing one, I'm missing gravitational energy for block 1. And it goes a distance up the incline of h. So it's gone up in height, h sine theta. All right, so we're almost there. We have one equation here, right? One equation. We can only have one unknown. We're trying to find V final, the speed of the blocks just before block 2 hits the ground. And I've got some things here I need to deal with, right? I've got an I and an omega. So let's take a look at those. Well, we can look up or calculate. We were given that it's a solid disk. We're given the mass and we're given the radius. So we can figure out what I is. That's a known. We'll talk about that more in a minute. One half mr squared for a solid disk. How do we get that? We look it up on the table in the textbook or on the formula sheet. Like I said, we'll talk about finding rotational inertias more after we finish this problem. So I is a given, we know that. What about omega? Omega and V are connected together because the string over the pulley causes the pulley to turn. If the block moves a certain distance, that's how much string moves across the rim of the pulley. They are related. The string is actually moving at a speed that's equivalent to the tangential speed at the rim of the pulley, right? How fast is the rim of the pulley moving? That's how fast the string is moving. That's how fast M1 and M2 are moving. So omega, how do we get omega? We get it from the fact that the tangential velocity at the rim of the pulley is equal to R omega. So V final is R times omega final. We plug that into our equation. And we get it. If I'm just going to do this one term here, 1/2 I omega squared would be 1/2 times I, which is 1/2 M pulley R squared, times omega squared, which is V final over R quantity squared. And what do I get here? I get the R's cancel, and we get a 1/4 M pulley V final squared. Okay. So this is what goes in here for this term, right? And now you have one equation with one unknown, and that unknown is V final. You can solve for V final. Okay, so these techniques that we learned using energy conservation, for example, using momentum to solve problems. These techniques that we learned, we started out pretty simple, right? We had to because our view of the world was pretty simple. We didn't have the tools to do complicated problems, but we were learning techniques, and those techniques are now still applicable. Our equation stretches a little bit and becomes a little more complicated to account for more things. We had to learn how to account for friction, so we could include the work done by friction. Now our objects can rotate, so we've added another energy term, a rotational kinetic energy term. Next quarter, the objects can be charged, so you can have electric potential energy. We'll add one more term to this equation. You can still use it, the same techniques to solve problems, but the equation gets a little longer to account for these real world effects, these new things we're trying to account for and accommodate in our equation. Let's talk about finding rotational inertia. So we have a few techniques. The first thing oh, actually, no, don't want to talk about that yet. I want to actually calculate I. Let's calculate I. So we're going to do, we've already done a couple of these. Let's do case one, we already did. This is a uniform rod. Rotating by its endpoint. That's this situation, right, where this is the axis of rotation. And what did we get? We got one-third ml squared. Now this, we didn't have to actually do the integral because this is on the formula sheet. If you look on the formula sheet, the back of the formula sheet you get with each exam on my website, or if you look at the formula table in the book for rotational inertia, that's there, right? You could look it up in the book on that sheet and it tells you what a rod rotating about its endpoint is. So we didn't really have to do that integral. Let's take a look at another one. The next one we did, we started today doing this one, right? A uniform rod. Rotating about its center. All right, so this. And what did we get? We got 1/12 ml squared. Again, we didn't have to do the integral. We could have just looked on that table and there's the answer, right? We could have gotten it right off the table. Do you have the table handy? Let me bring it up. Let me share this with you. Okay, so this is what I'm talking about. This is the table. And you can see A here, a slender rod, axis through the center, 1/12 ml squared. You see that? And then right next to it, because it's a very common shape, a very common rotational inertia, is a rod rotating about its endpoint. I is 1/3 ml squared. They have that here. They have a rectangular sheet rotating about its center point. And then they have a rectangular sheet rotating about an axis that goes along one edge of it. They have a hollow cylinder, a solid cylinder, a hoop, a sphere, a solid sphere, a hollow sphere. Okay, all kinds of common shapes here. All right, so we can look these up. So here's the rod rotating about its center point, rod rotating about its end point. Let's go back to this, and let's come up with another example. A uniform rod rotating about some other point. How about this one? Here's our axis of rotation, and here's our rod. Was that on our formula sheet? No, it wasn't. It was not on the formula sheet. So the first thing you should do, look on the formula sheet, look in the table, see if the rotational inertia is given. If it is, boom, you're done. You write it down. But sometimes it's not there. This is one example. So what can we do? Well, we can integrate, right? We know how to integrate. Let's do that, and let's find the rotational inertia of this rod. I'm going to give you a minute, see if you can set up that integral. Did you pick some little arbitrary chunk of it? Call that dm. If you do that, then this distance is dx, and this distance is x. Because I picked the axis of rotation to be my axis of rotation. What did I say? Because I picked my origin to be my axis of rotation. I think that's what I meant to say. All right, so what's our integral look like? Integral r squared dm. R is equal to x. X is the distance from the axis of rotation from the origin to dm. So if you make the origin your axis of rotation, then it's also equal to r. And dm is lambda dx. And we're integrating from a to a plus L. Integrate over the whole rod from one end to the other. What do I get here? I get lambda x cubed over 3 evaluated from a to a plus L. Lambda is m over L if it's a uniform rod. And then this is going to give me an a plus L cubed minus an a cubed. Okay. Now, no. We integrate over the rod, right? We are adding up. The integral is just a sum, right? That integral sign stands for sum. What are we summing up? We're summing up all the DMs, little tiny chunks of mass that make up the rod. Well, where are the masses that make up the rod? Little chunks. They're between A and A plus L. There's no mass anywhere else, right? Oops, didn't want to do that. All right, we have another technique we can use. Very powerful technique called the parallel axis theorem. I'll make this its own. We'll come back to this, show that we could also use the parallel axis theorem. All right, parallel axis theorem tells us that if we know the rotational inertia for an object, for one axis of an object that happens to go through the center of mass. So here's an object, rectangular, flat rectangular board, and it's if I know the rotational inertia of this object about an axis that passes through the center of mass, like this. Okay, Then if I know this one, I can find the rotational inertia for any axis parallel to the one I know. So parallel means I can move my pen over to here, my axis of rotation over here, and I could find the axis of rotation of this thing rotating about a point through the edge, like this, because this axis of rotation is parallel to the one through the center. It's a little hard for me to do this. They have to be parallel, these two axes. So let's take a look at this situation here. Well, let's just write it out. I, about some other axis, a parallel axis, is equal to I center of mass plus md squared. This is the rotational inertia about an axis parallel to the center of mass. Axis. This is, use green. This is the rotational inertia about an axis of rotation through the center of mass. M is the total mass of the object. And D is the distance between the two axes. Whoa, what was that? Okay, it's easier than it looks here. Let's do, well, first let's do the example we know about. Let's pick something we know and show that we get the same answer. So we know this one. We know a rod rotating about its center point, right? We know what this is, right? This is I center mass is 1/12 ml squared, right? We've calculated it. We looked it up in the table on the formula sheet. Both times we got 1/12 ml squared. So given this, if we were asked to find this one, which we've already found, we know what it is. We already calculated it. But let's use the parallel axis theorem and see if we get the same answer. So we say I is equal to I through the center of mass plus the mass of the object times the distance between the two axes squared. Well, I center of mass is 1/12 ml squared. So if you're given a shape like this, what you do is you say to yourself, The prop. Need another prop. Okay, you've got a rod rotating about its end point, right? That's what we want to know. A rod rotating about its end point. So here's my axis of rotation, and here's my rod. The white one's the rod, the copper tube is the axis of rotation. So it's rotating about its end point. I can rotate it this way towards the camera. I'm just going to hold it this way. Rotating about its end point. So we say to ourselves, I can look up, I can't find, let's pretend I can't find this on my formula sheet. I know it is there, but we'll do another one where it's not there. You say, is there an axis parallel to this one that goes through the center of mass of my rod? Yes, there is. And is that on the formula sheet? Ah, yes, it is. It's 1/12 ml squared. So then I can use my parallel axis theorem to find the rotational inertia about this axis. Or I could use it to find the axis over here, part way between the two. Or I could use it to find the rotational inertia about an axis out here, because this axis is parallel to the one that goes through the center of mass. Any axis parallel to the one through the center of mass, I can use this theorem to find. Does it work on a three-dimensional object like a sphere? Yes, it does. Yes, it does. Okay, let's do it here. Let's make sure we get the right answer. The right answer we know is 1/3 ml squared. So let's plug in what we know. We know our center of mass axis gives us a rotational inertia of 1/12. We're going to add the mass times the distance between the two axes. And what is the distance between the two axes? L/2. In this case. So I've got a 1/12 plus a 1/4, which is 1/3 ml squared. Okay, now we're getting some confidence, right? We know that at least in this case, it worked very nicely. Let's do one more where we know the answer. It's not in the book, right? This one. We just did this one with the rod rotating about a point far away from its end point. We could do that one now. So if this rod rotates like this around, it forms a washer, right? A hole in the middle, and some material outside, right? As it swings around like this. So I is going to be I center of mass plus md squared. I center of mass is 1/12. And d, what is d in this case? A plus L/2. I'm not going to do it. I assume you can simplify this down and it turns into what we got earlier. Or you know what might be easier? Let's just pick a nice number for A and show that it works for some nice number of A. Like if A is equal to L, then it's easy. Then this would be an easy thing to figure out, right? Should we do that? So let's come back up here rather than doing a whole bunch of algebra to show that this is the same thing. Let's come back up here and say if A is equal to L, then we have this situation, right? Then I would be equal to, what would I be equal to? 2L cubed, that's 8L cubed minus L cubed. That's 7. 7/3 ml squared, is that right? Somebody check my math. And down here, if A is equal to L, we get a 1/12 ml squared plus A is L. That's 3 halves, right? That's 9/4 L squared. Got to multiply that by 3. We got 27, 28 over 12. That's 7/3, right? Is that what we got here? 7/3. Yes. Okay, so rather than doing all the math to show that it works for every A, let's just pick an easy A, like A equals L, and show that they work. In that case, we get the same thing. So I think you're seeing that this parallel axis theorem is fairly powerful with the formula sheet, right? The formula sheet has a few standard rotational inertia cases listed there, but that plus the parallel axis theorem gets you a whole bunch more. Not everything, not everything. What happens if I give you a non-uniform rod? Then you can't use that formula sheet anymore, can you? Then you have to integrate. But for a lot of cases, the formula sheet plus the parallel axis theorem gets you to where you need to be. All right, time for a 10-minute break. We will pause the recording and pick it up again in 10 minutes. Let's practice with this situation, this object. We've got the pendulum of a grandfather clock, looks like this. Axis of rotation. We've got our thin uniform rod. And then it's attached to a disc. Solid, uniform disc. This will be radius r. This will be length 2r. So for the rod, we'll use 2r and mass m. And for the disc, we'll use radius r and mass 2m. Go ahead and see if you can set that up. So what's the thought process here? Split this up into two objects, right? We've got a sphere, we've got a disc, we've got a rod. So the I for our pendulum is I for the rod plus I disc. Let's do the rod first. That's just a rod rotating about its end point, right? We look that up on our table or we integrate, but we know that that's 1/3 the mass of the rod, the length of the rod squared. The mass of the rod is just m, and the length is 2r. So I end up with 4/3 mr squared. Now let's do the disk. What are you going to use for the disk? Parallel axis theorem, right? We've got a disk rotating about an axis of rotation over here. We ask ourselves, is there an axis of rotation parallel to this one that passes through the center of mass? Yes, there is. And how far apart are they? distance d equals 3r apart. So we can use parallel axis theorem here. I center of mass. What's the disk rotating about its center point? This is a solid disk rotating about its center point. 1/2 mass of the disk times the radius squared. And we're adding to that the mass of the disk times d squared, which is 3r squared. And the mass of the disk is 2m. I got 19. We okay with that one? Okay, if I have 2 hoops, one of them has a string or ribbon wrapped around it that's connected to the ceiling. And I drop them. We want to see where they land and which one hits the ground first. Okay. Let me share this. I made a video of this for you. This is one of 2 identical hoops I have. If I release it from rest, where will it hit the table? The orange marker is directly below the hoop. Pause the video and make a prediction. Okay, I'll give you 10 seconds. We ready? Let's see, where is it going to hit the table? Once more in slow motion. Falls straight down. This is my other hoop. The only difference between the two is that this one has a ribbon wrapped around the outside. If this hoop is released when that ribbon is attached to the ceiling, or in this case my hand, where will it hit the table? Will it land directly below the release point, or will it swing off to the left or right? Pause the video and make a prediction. Okay, this one maybe requires a little more thought, maybe not. I'll give you a minute. I have a lot of these shirts. I didn't plan it that way. Okay, have you thought about it? I'm going to let go of that hoop. Let's see where it hits the ground.
Once more in slow motion.
Okay, where is it? Directly below. Fell straight down. Does that make sense? Draw a free body diagram for each of these objects. I'll do the easy one for you. You do the other one. It also has the same downward force. What else does it have? Tension up, which is going to create some torque, cause it to rotate. But that's it, right? Am I missing anything? That's it. In what direction are those forces? Are any of them side to side? Any of them left and right? No. So how is that spool going to move left or right? It isn't. It isn't. It's going to drop straight down. Which one hits the ground first? If I drop them both at the same time, which one hits the ground first? Just look at the free body diagrams. They both have the same force pulling them down, but one of them also has a force pulling up on it. That's going to slow it down a little bit, right? That's another way of thinking of it. Yeah, it's a good way of thinking of it too. One of them, all of the energy goes into translational energy, moving fast. The other one, the energy kind of splits. Part of it is going into rotational energy, part is translational energy. Well, let's see. Let's make sure.
I'm going to drop the two hoops at the same time. One has a ribbon that's attached to my hand, the other doesn't. Which one hits the ground first? Pause the video and make a prediction.
Oh, sorry. Thank you. Yeah. Forgot to. New share. Forgot to share it with you. Okay, we ready?
Once more in slow motion.
Clear? Okay. Rolling. Should we talk about rolling? Rolling is actually fairly complicated motion, but there's sort of a simple way to think of it, and that's what we're good at. I'm going to try to convince you that we can think of rolling in a simpler sense, in a simpler way. So first of all, what is rolling? Rolling is this situation, right? We've got our object rolling along the ground. The part that's in contact with the ground, that's actually the axis of rotation. What happened to my? There we go. That's the axis of rotation. The object is spinning, right? And that point that's touching the ground is the axis of rotation. And that point is not moving at all with respect to the ground, is it? It's not moving at all with respect to the ground. If I move up to the center of the object, the center of the wheel or disc or whatever this is, it's moving with some speed. We'll just call that V center of mass because that's the center of mass of the object, right? Call that V center of mass. And that means that a point on the rim of my wheel, how fast is it moving? Twice as fast, right? Because it's 2r away from our axis of rotation. Our axis of rotation is the bottom point there where it's touching the ground, right? That's the axis of rotation. This thing is rotating about that bottom point. So the point at the center of the wheel is a distance r away from the axis of rotation. A point on the top is a distance 2r away from the axis of rotation. So it has a translational speed that's twice as much. That's rolling. That picture right there is what rolling is. That's kind of complicated. So let's see if we can break this up into simpler things. If we have, let's just think about what is pure translational motion. That means that this thing is just translating. It's just moving. How's that? Okay, now I'm all set. We're going to break this up. Pure translational motion. The whole thing is just moving, right? It's need another prop. Pure translational motion is this. The whole thing is moving without rotating. So the bottom part, the center of mass, let's pick a point. Center of mass is moving with speed v center of mass. The bottom point is moving with speed v center of mass. The top point is moving with speed v center of mass. Every point on it is moving with the same velocity. The whole thing is moving without rotating. What does pure rotational motion look like? Looks like that, right? The top is moving to the right, bottom to the left, and the center is not moving at all. If I spin it at just the right rate, I can get the top to move with v center of mass to the right. I can get the bottom to move v center of mass to the left, and the center there is not moving at all. Now, what if I combine these two? If I add them together, pure translational motion plus pure rotational motion. What do I get? At the bottom, where it's touching the ground, I get v going one direction, v going the other direction. I add them up, I get v equals 0. One of these, the center of mass is not moving. The other one, the center of mass is moving. I add them up, I get v center of mass to the right. And at the top, they both have the same velocity. I add them together, I get twice that velocity. What does that look like? Rolling. Looks like rolling, right? I take pure rotational motion and pure translational motion, I add them together, I get rolling. So instead of thinking of an object rolling as this complicated situation where an object is rotating about a point that's in contact with the ground and having to use parallel axis theorems and all of this stuff, I can just say this object that's rolling, I can magically in my mind split it into two objects. One that's just spinning without moving and one that's moving without rotating, and just treat them that way. And it's much easier to solve problems that way. But there's something that connects them. There's something I need to spin. The one that's spinning, the one that's translating is easy. I can just have it moving at the same speed that the object's center of mass was moving when it rolls, right? That's easy. I can just pick that same speed. The one that's rotating, I have to pick the corresponding angular velocity that matches how fast it would spin if it was rolling, right? So something has to connect these two. And that's what we're going to talk about right now. What connects these two? I've got a wheel here. One side is in contact with the ground. So let's call that point A right there. Point A is in contact with the ground. And point B is up here somewhere. And I'm going to get my paint out, and I'm going to paint the rim of my wheel between points A and B. I'm going to use my green paint here, and I'm going to paint the rim of this wheel between points A and B with green paint. And now I'm going to roll that wheel forward until point B is touching the ground. So over here, point B is touching the ground, and point A is up here somewhere. And how far has it moved over? This distance, right, is now all green here, right? So let me write here. This is some arc length S, right? What is this distance? It's the same. It's the arc length, right? It's the, look at the green stripe, right? You're going to end up with the same distance. The point I'm trying to make is that the center of mass of my object moved forward by a distance s. So the v center of mass and the velocity on the rim also moved by a distance s in this same time, right? So they're connected. The velocity of the center of mass is equal to the velocity on the rim of the wheel. And the velocity on the rim of the wheel is r omega. So the velocity of the center of mass is equal to r omega. That connects the angular velocity and the velocity of the center of mass when we have rolling without slipping. When the wheel rolls without slipping, there's a connection between how fast the center of mass is moving and its angular speed that it's rotating at. And this is that formula. This is the connection. The velocity of the center of mass is equal to r omega. If there's slipping involved, then anything, we don't know. Anything could be possible. There's no connection anymore between these two. Okay, let's do an example. I think the easiest thing is just to do an example. Let's have a ball rolling down a hill. Let's make it a hollow ball, like a basketball. And we know the height that it starts out. Well, let's see, we have to know more than that. Given, the ball rolls without slipping. The mass of the ball, the radius, V initial is 0, starts from rest, And we know h, the starting height. Find the velocity of the center of mass at the bottom. So this looks a lot like energy would be a good tool here, doesn't it? Mechanical energy at the beginning, mechanical energy at the end. Are they going to be equal? Do we have to account for something? They are equal. Normally we have here, what do we have? Work done by friction. Do we have friction in this problem? There has to be friction. If there was no friction, what would the block, what would it do? It would slide down the hill, right? It wouldn't roll down the hill. So there has to be friction. But what's the work done by friction? Zero, because what kind of friction is it? Static friction. It does no work on our ball. Now is probably a good point to talk about something called rolling friction. Let's have a little aside here. There is something called rolling friction. If you've bought tires for your car recently, maybe you've thought about this a little bit. Some tires advertise that they are high mileage tires, or they get you, your car will get better mileage with those tires than with other tires. They're talking about reducing the rolling friction. So when a wheel rotates, let's just, let me see if I can. There's a wheel. There's the ground. When that wheel rotates, a real world wheel deforms a little bit as it rotates. As it rotates, there's some deformation that happens right here. The wheel, the rubber that makes up the tire gets squished a little bit, right? And it forms sort of a bump right here. It forms like a, the rubber bunches up a little bit right there, deforms a little bit. And so there's a number of ways to think of it. It's almost like your car is always driving over a little bump because it's forming a little bump right in front of the tire itself. Another way of thinking of it is that that rubber gets squeezed together and then it goes back to normal, and more rubber gets squeezed together and goes back to normal. What happens when you squeeze rubber and let it expand, squeeze it, let it expand? There's friction, internal friction, and the rubber heats up a little bit. Well, what does that mean? That means energy is coming out of your car. If you start a wheel rolling on a perfectly horizontal surface and there's rolling friction involved, that wheel will eventually slow down and come to rest. We will dissipate the mechanical energy into the deformation of the rubber, the heat that the rubber warms up, right? Things like that. But in our cases, we will not deal with rolling friction. What we're going to say is that our wheels are perfectly rigid. They do not deform at all. The ground is perfectly rigid. It does not deform at all. And if you had a wheel that was perfectly rigid, that didn't deform at all, and you got it rolling on horizontal ground that did not deform, rigid ground, it would keep rolling forever. We would not lose any energy to the static friction that causes it to roll. Okay? So this causes what do they do on those tires? I assume they make the sidewalls stiffer. If the sidewalls are stiffer, then as you drive, the tire doesn't deform quite as much. And so you get better gas mileage on those low rolling friction tires. All right, why static friction? Because the object is not sliding, right? If the wheel is turning or our object is rolling down the hill, then the point of contact between our wheel and the road is not moving, right? There's no motion between those two. See, look at my finger that's in contact with the road. It's not moving with respect to the road. If there's sliding, if it's doing this, sliding down the hill, then there's kinetic friction, right? There's sliding, there's motion between the two. But there's no motion between the surface of the wheel and the surface of the road. They are static. Otherwise, we have sliding. Well, static friction doesn't go through a distance, right? You're thinking about work done by friction. It's the force of friction times the distance through which that force acts. Well, static friction doesn't act through any distance. So it's not doing work, just like the normal force isn't acting through any distance, right? The object isn't moving up or down off the incline, so the normal force isn't doing any work. Static friction isn't acting through a distance. I guess that's one way to think of it. Okay. All right, so that's rolling friction. So we will not deal with rolling friction in this class. Our objects will be rigid. That means we can do energy conservation. So initially, we're going to say E initial is equal to E final. Initially, we have all gravitational potential energy. Nothing's moving, M, G, H. And at the end, this thing is rolling along the ground. And we said rolling is kind of a hard thing to deal with, but we can magically in our minds split this into two identical objects. One that's translating without rotating and one that's rotating without moving. And so we're going to do that. We're going to say that this is the same as having translational and rotational kinetic energies. The translational is just 1/2 m v center of mass squared. That's how fast the center of mass is moving as this object rolls along the ground. And the rotational is 1/2 I omega squared. Now this is one equation. We can only have one unknown. So we have to turn omega into v. But we know when something is rolling along the ground without slipping that there's a relationship. Omega is v center of mass over r. And what I are we using? Well, let me do one thing at a time. V center of mass is our omega, or omega is v over r. And I, what is I? That's the rotational inertia about the center of mass. Not the point that's touching the ground. We've eliminated that. That's, if you really want to think about rolling properly, you would need the rotational inertia about the point that's touching the ground. That's where it's rotating. But we said we can break up the motion into pure translation, something moving, and pure rotation about the center of mass. So this I is the I for the center of mass of our object. All right, so let's plug in what we know here. We know that we have a 1/2 m v center of mass squared. We have a 1/2 I. I is 2/3 mr squared. You look that up on your formula sheet. And v center of mass over r is what we're using for omega. That's squared. I get 5/6. And we can solve for v center of mass. Okay. So we were talking about it up here, how we can deal with rolling. It got a little complicated. I think if you see it in action, it makes a little bit more sense. But the reason we can do this is because of what we talked about up above. We've got this complicated motion, something rotating about a point that's in contact with the ground. But instead of using that, we split it up magically into two identical objects, one that's just moving, 1/2 mv squared is its kinetic energy, and one that's rotating about its center of mass, 1/2 I omega squared. And it's a little easier to deal with that way. So we're getting to that point now where we can deal with, it's getting more interesting here. We've got real objects rolling down hills. We've got pulleys that have mass. We're able to deal with a lot more real world situations now. Okay, this is a good stopping point. Next time we will do some angular momentum. That's the counterpart to translational or linear momentum. And that helps us get through collisions, because things that are rotating can also collide, right? You could have somebody on a big platform, like one of those merry-go-rounds at the park that the kids play on, run and jump onto that and start it rotating. That's a collision, right? We can figure out how fast it's going to be going. We can have a pendulum swing down and collide with something, not just a point pendulum, not just a simple pendulum, but a real one with a bar as a rod with mass, with something colliding with that, a physical pendulum. Anyway, we will deal with that next time. So I'll stop the recording. I'll stick around, see if anybody has questions. There's always office hours at 4 o'clock, but I will stick around and answer some questions for a few minutes.